So I'm sticking to English, so that everybody can. Well, I guess all the French speakers can understand, and of course the possible non-French speakers will hopefully understand as well. So so yes, I'm going to present you this work on self-supervised multi-frame denoising and super resolution. This is a joint work with a lot of PhD students and postdocs. So Valérie Deville, who's a PhD student, Ngoc Long Nguyen, who's also a PhD student, Jérémy Anger, who's now postdoc, Axel Davy, also postdoc, Thibaut Herré, Paulo Arias, who's not only postdoc, he's also a director. He's co-directing all these jobs that I'm presenting. And of course, Jean-Michel Morel, who's always giving his blessing with his advice on all these works. So let me move forward, and don't hesitate to interrupt me if I'm going too fast, too slow, or too imprecise. So the idea of this work is to present you this notion of learning in a self-supervised way without clean labels. So let's suppose that we are given a video with unknown noise. So our initial task is going to be video denoising, and we're going to show how to take this video and to learn a denoiser that can denoise it from a single video, so without any ground truth label. And so this is going to essentially leverage two concepts. One of them is noise to noise, which probably most of you know already, but otherwise I will explain it anyway. And then the fact, the redundancy of the frames. So noise to noise needs 2 frames, and videos has lots of pairs of frames. So every consecutive frames is an opportunity to exploit the noise to noise constraint. And then we are going to move this. So in the presentation, I'm going to present noise to noise, frame to frame, which is a first version of a video denoiser that learns from this video. Multi-frame to frame, which extends this concept to multi-frame networks. And then I'm going to present DSI self, which is a multi-frame super resolution technique that also resembles a little bit multi-frame to frame, but you will see that it's quite different by construction. And so we applied this on satellite images, and hence the remote sensing. So let's start. Why self-supervision? So the reason why we care about self-supervision comes from, in a way, it's kind of summarized very well on this paper from Plots in 2017, where they show that actually neural networks trained on simulated data perform very badly on real data. And to the point that BM3D, a classical method from the literature, state of the art, but classical, it's much better than these networks. So the problem here is that there is a domain gap, which is the difference between the simulated and real noise. So real noise is slightly different. And CNNs tends to learn very well to denoise their task, so the simulated noise. So how can we train with more realistic noise? So there are different approaches to this problem. One of them is to improve our simulated noise, so make it more real. And so people have been proposed in several occasions networks that produce more realistic noise, that reproduce more in detail the acquisition pipeline and all the physical characteristics of noise. But there's a problem here, is that if we don't if we don't master the pipeline to the perfection, we may introduce a bias, and so our network will be subpar. So Another possibility, which is probably the preferred one from the practitioners, is to do, well, let's take ground truth data. And so this is very expensive, of course, because for photos, you can take a couple of photos, one with long exposures or another with shorter exposure. But this is very time consuming and also arguably more demanding than the first approach. And it can be very impractical or even impossible for certain applications like video, because we cannot ask people to stick to stay quiet to do a double exposure acquisition. And so we get here to the point of, okay, let's try to get rid of all this with self-supervision. And so the idea, well, all of us should remember the olden times when people didn't have ground truth for their data, or they used it just for validation, but they designed methods that just optimized a certain energy. And so these fall perfectly inside the self-supervised category. What we are going to say in what we are going to focus on is a self-supervised setting in which we ask the network to produce something that is close to the input data. Of course, this is not a very well stated problem, because the optimal solution here is the identity, so we don't do anything. But we will see that with a little bit of ingenuity, we can solve this problem much better. And so this brings us to the self-supervised area, or self-supervised domain, which kind of started with it started with noise to noise, probably. I cannot state it as a fact, but noise to noise really bootstrapped this tendency, and now there has been a Cambrian explosion of methods that are something to something with noise in some way. So the idea of noise to noise, I won't go through all of these techniques, but the idea of noise to noise is really, really simple. So let's first step back and look at what a supervised training would do. In supervised training, what we do is to minimize the empirical risk of this form. So we have a loss between the output of the network and some ground truth label U. We know that this empirical risk converges to the risk for an infinite amount of labeled data, and we can say that, well, we can derive from this information. So we can derive the optimal estimators for this kind of problem, which is depending on the loss that we choose, we end up having a minimum mean square error estimator for the L2 loss. So this is the expected. So the conditional expectation of all of clean images given the noisy observation. Or we can, if we choose the L1 norm, we have the conditional median, or with the L0 norm, we have something close to the conditional mode, or the maximum posteriori for this kind of problem. So this is just estimator theory that we have. It's a given for the clean label case. The fancy part here is when we introduce noise to noise. So noise to noise proposes the following. So instead of having a label that is a clean observation, we suppose that we have another noisy observation here, Z, and we are going to optimize using this noisy observation as label. And so we'll end up having this empirical risk as before. And this empirical risk, the optimal estimators for this empirical risk end up being just the minimum mean square error, but of the noisy signals given the other noisy signal. So this is weird. So we are just asking, give me the average, the average expected noisy signal given this other noisy signal. The same for the median. So for the L1 norm, we get an empirical conditional median and a conditional mode for the L0. This is all covered in the Lehtinen paper, noise to noise. So what is not said yet is that this empirical median doesn't say anything about, a priori, they have no relation to the clean problem, except for the fact that they do. Actually, the main result of the Lehtinen paper is that these conditional expectations, at least for the case of for the L2 norm, the conditional expectation of the noisy signals correspond to, sorry, this is the thing I should point out. The conditional expectation of the noisy signals gives the same result as the conditional expectation given obtained using clean signals, clean labels. This has a condition. The requirement is that the noise has zero mean. So we must so the expectation of the noise observation given the clean one converges to the clean signal. And so we have similar results, but which are less strong. Actually, their proofs are more hand-wavish for the median, for the L1 norm, and for the mode. But empirically, they can be verified. They actually converge. So what does this mean? This means that at least for L2 and L1 norms, we can train with a noisy target, a noisy label. And in the end, if some mild assumptions regarding the perturbation, the noise, are verified, then we will have the same behavior as the original labeling, as the original noise to clean task. And so this is verified in the Lehtinen paper. They show that essentially training with noisy or clean labels, they attain very close performance in very different denoising tasks. So this is great. They showed this, and they also used pairs of images to train the denoisers. So you can imagine taking couples of photos for each one of these. Every time you need to train, you need to take a couple of photos, align them, and train a denoiser, which is great, but still impractical. And that's why we thought, okay, let's try to. It's not it's not a very long stretch to observe that in video there are pairs of photos every 30th of a second. So we can actually use the time consistency, the consistency between consecutive frames, to train a noise-to-noise like method, which we called frame-to-frame because, of course, video. So here the idea is to take a couple of consecutive frames, feed one to a network, and compare it with some version of the previous frame or the next frame. So this, assuming that the video is static, this is immediately noise-to-noise, and we have plenty of frames. If the video is moving, then we'll have to compensate for motion. And so here is the schema of noise-to-noise, of frame-to-frame, sorry. So we take a couple of frames, t and t-1, and behind the curtain, we apply an optical flow to these two frames to try to align them. This optical flow, of course, may fail at some parts, and so we have we designed a block that tries to remove these mismatched areas. So then one of the frames goes through the denoiser, which is trained in this case. So we will try to denoise this frame. And after denoising, we will warp it according to the optical flow. This warped frame is then compared with the previous noisy frame. So we have a match. And of course, the loss will mask out the misaligned parts. So putting formulas, it's probably much clearer. Here we see the current frame going through the network, being warped with the W, and then compared with the previous frame. And this is the loss for this frame, which is masked by the mask that we derive with some empirical rules that gives the mismatched pixels. And so the training for training these networks, we train them starting from a pre-trained network. I won't enter too much in these details, but if we don't start from a pre-trained network, actually the task is not very well learned. But we can fine-tune these networks on a single video, and they actually improve much better. They go from a noise that is not really carefully chosen. They go perfectly to the noise that we synthesized for these experiments. And so this fine-tuning can be done online, so as we consume frames, or it can be done on a set of videos to get better, to obtain better performance. Let me just add a little detour here regarding the mask. So this mask is really important because if we don't mask out bad pixels but corresponding pixels, then the network will be forced to learn something from them because they will enter the loss, and we will say, okay, in the optical flow, evidently this scatter is moving too fast, and the optical flow mismatched all the limbs, and so that's why everything is kind of fuzzy in this result without mask. With mask, we say, okay, don't learn anything here. It will be learned from other frames in the video. So that's just a detour, and that's pretty much everything that I need to say about frame to frame. It works. It is quite good, and it can be extended to demosaicing as well, because we can mask out pixels. I just have this slide for the mosaicing because I just want to mention the fact that we have a lot of control over the loss, so we can mask out pixels, and just by this trick of aligning the reconstructed image with the noisy label, it's enough to learn the task. Here is join the mosaicing and denoise. So now I'm going to show. So this, I'm not showing results of frame to frame, because frame to frame, although the idea is quite neat, it's a single frame denoiser. So taking an image from a video and denoising it is kind of suboptimal, because the network, the underlying network or the algorithm, doesn't exploit the fact that the video is redundant. So there are many redundancies in the video, and so any algorithm that tries to do video denoising should not try just to denoise a single frame. It should ingest several frames at a time, arguably as much as possible, so to obtain a better result. And so in this work, what we did is to take this concept of frame to frame and extend it to multi-frame to frame, and try and solve solve the problems that come up with this setting. So here is the diagram. I won't explain it too much because I'm coming right away. So the idea of multi-frame to frame is to take a network that is a multi-frame network. Here we use FastDVDNet. FastDVDNet is a cascade architecture that takes 5 frames so the frame t, and 2 frames in the future, 2 frames in the past, does a set of units to produce an output. We will use it as a black box, but I wanted to mention that it is this architecture. So now the task, the question is going to be, okay, let's take these 5 input frames, feed them to a network, produce some result, and we'll have to compare it, this result, which will be a denoised version of frame ft. Let's compare it with some warped version of another frame. So which frame? Should we take ft minus 1, ft plus 1, ft plus 2, or which frame? So, and here comes the observation. So our first experiments were like this. We did try ft minus 1, and we stumbled upon this observation, which is classical as well in estimation, but we didn't actually foresee it at the beginning. Is that if we train a network with a label that is a function of the input, then in that case, we don't learn anything from the data. So actually, our result doesn't depend on the distribution of P of the noise observation given the clean one. This is a very, very important observation. And so in other words, if our label is a function of the network input, we are not data driven. We are variational to some extent. So we are going to have some denoising, but we won't be data driven, and the performance will be much, much lower than what one would expect. Another way to see this is if we use ft minus 1 as the target of this network, then the network will learn to warp the input frame to the output. It will try to apply a warping and not to denoise it, because denoising it won't close the gap. Sorry, it will denoise it a little bit, but it won't denoise it as much as if the input frame was available. Because, sorry, let me state this in a different way. If we say, let's take this input stack and the target is ft minus 1, the network will learn a path of the data so that this frame will be channeled to the output. And that will minimize the loss. Although it will be warped, it will minimize the loss. And if we shuffle the frames, a similar result will be obtained, just blurrier, but bad in any case. So the bottom line is the input must not contain the target frame. And so for the training stack or the fine-tuning stack, we have to either spread out or move one frame apart to make sure that the input doesn't contain it. So here the blue frames are considered as input in this dilated stack input stack, and ft minus 1, which is closer to the input, is going to be used as loss. So we use this for training, or we can use other variants as well, because they all perform similarly, as long as the next frame, the frame used for the comparison, is the closed one. And we train like this. And for inference, we use a consecutive stack. So we don't use the deleted version of the stack. We just use consecutive frames. And this works very well in practice. And here we can say, so after training, we can see that different noise characteristics, so Gaussian, Poisson, box noise, which is a sort of correlated noise, or even the mosaic noise, they all perform very well on this offline multi-frame to frame network. Sometimes even better. So in some situations, even better than the supervised network, as the supervised gold standard will say. In most of the cases, the gold standard is not attained. It's just, we are just getting closer to it. So that's it for the multi-frame to frame. Here, are the idea. I started with the idea of having real noise being denoised. So here we are taking a data set of real noisy videos and showing you just a couple of frames, showing that the result is actually much better than a state-of-the-art method. So RDVNet is a network that has been trained and published to show that they can denoise very well real videos. See here on the right, and by applying this technique, we get a much better result qualitatively, because these are real images, and so we cannot actually measure this quantity, but it is really well. We see a lot of details, many more details in these images, and these are not hallucinations. They are consistent in time. So I'm about to end my time. So yeah, so let me go quickly over this multi-frame, multi-image super resolution. So the idea here is to take this idea and to put it in space. Let me just tell you about SkySat. SkySat is a push frame satellite. So the satellite is just taking a video of the Earth, and this takes 40 frames per second. And the interest of these frames is that they are aliased, and they all see the same point on the spot on the ground about 15 times. For every point on the ground is seen 15 times. And so here it comes naturally. It's part of the design of the satellite. Let's do super resolution. And here what we propose is a super resolution method that is self-supervised, so that is trained without any labeling data. So this is a work that Long presented at this workshop CVPR in this year. So the idea of the core idea that comes from the self-supervision is that since we have a lot of frames, let's do what we did before. Let's take a stack of frames, pick one apart. So take one reference apart. This is very important because, as we remember, otherwise we won't learn. Let's feed it to some network, get a super resolved result, then downsample it. So we are applying the forward model here, downsample it, and compare it with downsample it and align it. Sorry, align it and downsample it. Sorry, the downsampling will just take care of the aligning, and compare it with the target frame, which is the withhold reference. So this idea is essentially, you can see the layout of this concept of having a training that is using a noisy label. And so for that, we develop an architecture that is based on a very classical super resolution pipeline, which is called a shift and add, which consists essentially on taking all the frames, aligning them, registering them, stacking them, and aggregating the samples on a finer grid. We replace all these components with fancy neural networks, a network for the estimation, a network for the fusion. So we use features for the fusion, and this gives this diagram, which I can explain is not as complicated. So as we pick one reference apart, we try to align every frame to the reference with this motion estimation module, which is trained end-to-end in the network. At the same time, every frame is encoded, and this encoding vector is aligned with the optical flow and stacked or aggregated in this feature shift and add block. This feature shift and add is not trainable, so the only blocks that are trainable are the red ones. So this shift and add is just aggregating the information, and the decoder then reconstructs an image, which we will then downsample to compare against the reference. This is at training time. I'd like to point out the fact that this is a network that is permutation invariant by construction. Unlike the FFDNet, here I can have as many input frames as I like. So at inference time, I can I don't need to encode I don't need to pick apart the input frame. The reference frame, I can feed it also to the shift and add module. And this gives a little boost on the performance. So as you can imagine, there are losses here. I will, in the interest of time, I will just skip them because, yeah, pretty much over. So there is a self-supervised loss, and also a loss for controlling the motion, the motion estimation, which is just optimizing the alignment between the work frames. And that's it. And let's go to the results. In the end, this method performs very, very well, to the point that it attains almost perfectly the performance of, in this simulated setting, it attains almost the performance of the clean, a network that is trained with the clean labels. So we take, well, it's simulating everything. So we have a high resolution target that we use for training, and the DSA self, which is the network that we train with self-supervision, attains almost the same performance. And the architecture, since it's very, very flexible, it performs much better than other neural networks, and of course better than classical methods like ACT. So, but how does this work in practice? I just have one slide here for showing you, but I think it's quite compelling. The idea is that we perform better than the product that Planet, the operator of SkySat satellites, is delivering to the customers. So this is the product, the super resolved product by Planet, and this is our super resolved product with a 3 zoom zoom, but it could be perfectly 2. So we just this is just to show off the fact that the network doesn't care about the resolution of the rendering, and we obtain nice smooth results. We can also I think this is not sharpened, but we can also sharpen the result with the network. So to wrap up the conclusion, we've seen how to self-supervised training several things, multi-frame videos. So with these works, we can also demosaic and also do self-super resolution. So these are all the works that I just presented. The benefits of self-supervision, just to stress them out, is they're model blind, so we don't care about the model as long as some conditions on the model are verified. We are sure when using them that there is no dataset bias. I didn't mention about the overfitting, but overfitting can be actually useful if we train on a dataset that is specific. So if we have many images over a site, we can train on them, and this overfitting will permeate the network and will perform slightly better on those images. Online learning is the fact that we can fine-tune online. And of course, there are some challenges that have to be addressed in the future. So we depend a lot on the good alignment of the input frames, and the temporal correlation of noise is something that I swept under the rug, but it's not to be taken at light, because if some of you work on infrared imagery, you'll know that the temporal coherence of noise is very common. So that part has to be taken care of. So that's it, and I'm open for your questions.
Merci beaucoup, Gabriele. Alors, on a un petit peu dépassé, je crois, par rapport au planning, mais on va quand même prendre une ou deux questions. Donc, les personnes qui veulent parler, enlevez vos micros et puis parlez. C'est plus simple. Qu'est-ce que des gens veulent poser une question? Je vais en poser une pour commencer. Dans le challenge, c'était peut-être pas un challenge, mais SkySat, j'avais une question. Est-ce que les images sont aliasées? Parce que oui, j'ai du mal à... Elles sont aliasées, d'accord, ouais. Sinon, on ne peut pas vraiment faire de super résolution.
Non, exact.
OK. D'accord. Ouais, j'avais une question aussi sur l'indépendance du bruit. Et donc, cette hypothèse d'indépendance du bruit entre frames est essentielle quand même pour le succès de la méthode.
Ah oui, 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 oui.
Et
C'est,
alors, en pratique, j'imagine que c'est pas le cas.
en fait, c'est pas le cas seulement pour les fixed pattern noise, non? C'est
D'accord.
les,
Non,
les-
c'est une question, hein, vraiment, je ne suis pas du tout
donc, non,
spécialiste.
non, le bruit, il est aléatoire parce qu'il est issu de la partie du bruit qui vient des bruits photoniques. Lui, il est bien indépendant. Le problème, c'est il y a des circuiteries, des circuiteries ou des process qui interviennent dans l'acquisition d'images qui, eux, ils ne sont pas complètement indépendants. Concrètement, des fixed pattern noise. Donc, les fixed pattern noise, il y a plusieurs niveaux de fixed pattern noise, mais un, c'est celui qui vient de la densité comment ça s'appelle? De la densité et la capacité de chaque pixel de récupérer des photons. Elle peut être légèrement différente, donc ça introduit un type de bruit. Et il y a aussi des bruits de lecture qui est assez régulier dans la scène, donc des bruits de lecture électronique. Donc, ces différentes sources de bruit, on peut envisager de les enlever. Donc, le fixed pattern noise, il est enlevé systématiquement de toutes les images satellites qu'on reçoit. Mais il peut avoir toujours un peu de perméabilité. Et pour ce qui concerne les bruits électroniques, là, il faut vraiment mettre quelque chose en pratique. Il faut développer. Pour l'instant, on ne l'a pas. Sur les images qu'on a, ce sont de vraies images KISAT. Il n'y a pas ces bruits-là. Mais si dans l'audience, il y aura des gens probablement qui font de l'imagerie infrarouge. Et là, en imagerie infrarouge, tout le temps, il y a ces bruits de lecture électronique, spécialement sur des capteurs non refroidis. Donc, ça fait des grands... Bon, pour ces publics-là, ils seront tous scandalisés. Mais bon, ça...
Merci beaucoup. Alors, je ne vois pas d'autres questions. N'hésitez pas à ouvrir votre micro si vous en
Il y a une
avez.
question de Mathieu Gallet.
Ah, alors, je vais la... Alors, la question est la suivante. Can we use the method of multi-frame for satellite images with a large temporal baseline, one image every 6 days?
Yes, but it will be a bit smooth, right? So you can, I can think of some way of detail transfer for for this setting. I would think of something like a detail transfer, because the images every 6 days will have some things that move a little bit. So that's not very good for the move or change, right? The radiometry may change a little bit. But you can imagine that what you care about with this super resolution is to have some sort of detail enhancement. And so what you can do is to run this on a high-pass version of your data. And that would essentially improve a lot the result. So I imagine that you're thinking of this probability challenge, and yeah, okay. okay, yes. So I will just do the question. So the probability challenge may be solved in this way. We didn't attack it with this self-supervision because probability has comes with a high resolution camera. But if you have a setting where you have an aliased satellite that takes one image every 6 days, that's fine. Well, yeah, I can't think of one of them. Sentinel on the bands that are not on the multispectral bands. Anyway, thank you. Good question. Eh? That's a very good question.
I have one more question if we still have time, Pierre.
Yeah, I think we have time anyway. So maybe je dis à tous les participants, si vous pouvez aller à la pause et on continue les questions. Vous pouvez aussi rejoindre les participants, les orateurs dans la salle wonder.me. Mais vas-y, Andrés, bien sûr, tu peux y aller.
Non, j'ai une question juste sur la première partie, sur les. Bon, d'abord, merci, j'ai bien aimé l'exposé. Et surtout, les deux parties, c'est complémenté très bien. Et donc, la première partie sur le débruitage, autosupervisé. Je crois que c'était slide 22, tu peux revenir.
Oui.
Et alors là, tu as mentionné un résultat dont je n'étais pas au courant non plus, j'ai appris une chose. Donc, tu disais que si le label dans la loss contient une fonction de données, et donc tu ne prends pas vraiment la distribution que tu veux. Mais ça, si je ne me trompe pas, c'est le cas dans le cas précédent où tu calcules le masque. Enfin, tu calcules le masque.
Quand je calcule le masque, non, pourquoi?
Le
La
masque
masque,
ne dépend pas.
il n'est pas appris. Le masque, il n'est pas appris. Hein. La masque,
Le masque, il n'est pas appris, donc il ne dépend pas de données. D'accord, j'ai mal compris. OK.
Pour rebondir un peu, je clarifie une chose. Ce résultat-là, on l'obtient avec l'hypothèse de que le réseau il a la capacité de mémoriser les résultats pour chacun des inputs. Donc, si le réseau il a un goulot d'étranglement, là, il y a une sorte de régularisation dans l'optimisation. Et donc, le résultat, il ne sera pas... On aura un résultat peut-être mieux.
D'accord.
Donc, c'est ça.
Très bien, merci.
Merci à toi, c'est une bonne question.